Dynamic amplification is a measure of how much structure's response, displacement velocity acceleration is amplified due to the effect of waves. So what we are going to try to see is that how much the structure response could be anything like displacement velocity or acceleration that is going to be amplified due to the dynamic effects of the waves. So that's a measure. Dynamic amplification factor means it's just a measure of that how much is going to be amplified. It accounts for the resonant interaction between the platform's natural frequency and the wave frequency, which can lead to higher than expected responses. So that usually the resonant interaction can lead to higher than expected responses. Understanding the DAF is crucial for ensuring the structural integrity and safety of marine structures like offshore platforms, ships, and floating systems. Here we can see the basic formula of DAF. Here you can see 1 divided by square root of 1 minus TS by TW or square. Sometimes this ratio is called the natural frequency ratio, they used to say. The natural TS is the natural period of the platform. It's intrinsic oscillation period when subject to external forces. TW is the wave period, that's a period of waves passing over the platform, and C is the viscous coefficient, damping coefficient, which represents how much the structure resists oscillations due to energy dissipation. Physical interpretation, if you see the DA formula describes the amplification effects due to the resonance phenomenon. If the wave period is close to the natural period of the platform, the oscillations of the platform can become much larger due to the resonance effect. So oscillations of the platform can become much larger due to the resonance effect. In simple terms, when the frequency of the waves matches with the natural frequency of the platform response is amplified. So response is getting amplified when the frequency of the waves as well as the natural frequency of the platform are matches. The damping coefficient represents how much energy is lost to friction or other resistive forces within the platform, which reduce the potential for amplification. So usually the damping reduces the potential for amplification. The larger the difference between TS and TW, the smaller amplification effect. However, when they are close in value, resonance can lead to a significant increase in platform's oscillatory response, thus a higher DAF. Here we can see amplification factor in wave direction, like DAF is square root of DAF in 1 square cos theta, DAF 2 square sine square theta. Like theta represents the wave directions, DAF1, DAF2 amplification factor along the specific directions of wave motion. Physical interpretation, if you see, waves often approach the platform from different directions, right? And the structure's response to these waves will depend on how aligned the wave direction is with the platform's natural motion. If the factor DAF accounts for how the amplification varies as a function of wave direction. So this factor, it accounts for how it varies based on the function of wave direction. This expression uses cosine and sine of the angle to the weight of amplification factors in two main directions, principal axis of the structure. This means that the platform's response will be more amplified when the direction is aligned with the platform's natural oscillation direction. The formula essentially provides a way to compute the overall amplification factor, taking into account the different directions from which the waves may approach, how those directions contribute to the total dynamic response of the platform. In essence, DAF is the key factor used to predict how much the dynamic response of the platform will be amplified wave forces. The first formula reflects how the platform's natural frequency and the wave frequency interact with the damping, helping to mitigate the amplification. The second formula takes into account the influence of the direction of the wave motion on the platform's response, and combining the directional amplification factors using trigonometric functions. Understanding and calculating the DAF ensures the platform can be designed to withstand the potential large oscillation due to wave action, ensuring safety and stability in marine environments. We can see one example: natural period of the platform 10 second and wave period 12 second. Viscous damping consider 0.02, that's a 2%. We will first calculate the DAF using the first formula. So if we plug in the values into the formula, we will get TS by TW and then square this value. Now substituting everything into the formula DAF, we can get the DAF value. We can simplify the equation, and these factors we can calculate the second term and multiply by 4. Now once multiply all these factors and calculate DAF, it comes to be around 3.25. Dynamic amplification is approximately 3.2. This means that the platform's response is amplified in factor of 3.25 compared to its static response when exposed to a given wave conditions.
Suppose we are considering the wave direction. Let's say the platform experiences a wave coming at an angle of 30 degrees. To calculate the amplification factor in this direction, we use this formula. Let's assume that df1 3.5, df2 is 2.8, the wave direction is 38. So we can see cos 38, sin 38, the cosine and sine function. Now once you substitute these values into the formula, we can get the value around 3.34 for that's for the 30-degree angle. Now see a discussion introduction to DAF. Today we are going to learn about something crucial for marine structures, dynamic amplification factor. It's a measure of how much the waves amplify the response of the platform. It's nothing but how much is a measure of how much the waves amplify the response of the platform. If you are working on offshore platforms, we need to understand this concept. What exactly do you mean by dynamic amplification? So what exactly do you mean by dynamic amplification? Are we talking about the platform moving more because of waves? That's the question from Alex. Yes, Alex, exactly. Dynamic amplification happens when the natural frequency of the platform is close to the frequency of the waves. Imagine if you push a swing just at the right time, it goes higher and higher. That's the resonance. When the wave frequency matches with the platform's natural period, the platform's movements gets amplified. If it matches with that one, it gets amplified. This is critical to understand the stability and safety. But if the waves are random, how do we calculate the platform's response? How do we know when the resonance is happening? Good question. This is where the formula comes in. It helps us predict how much the platform will oscillate when exposed to the waves. This is the formula. So wait, what are the TS and TW and what's that C? Great follow-up. TS is the natural period of the platform and the time takes to complete one oscillation. TW is the wave period, the time it takes for a wave to pass a given point. C is the damping coefficient, which tells us how much the platform resists oscillation due to internal forces like friction. So if the wave period is close to the natural period, we get higher amplification, right? Yes, exactly. That's why we need to be careful when the wave period is close to the platform's natural frequency. And this is what the formula is calculating. How much platform will amplify the wave effects. What happens if the waves hit the platform from different directions? Does it amplify in the same way? The direction of the waves definitely matters. If the waves come at an angle, they interact with the platform differently. We calculate the amplification in different directions using this formula. Yes, so theta is the wave direction, and but what's df1, df2? Theta is the angle of wave direction, and usually measured in degrees. Like df1, df2 represent amplification factors along the principal directions of the platform. The formula combines them based on the wave direction to get the amplification, total amplification. But why do we use sine and cosine? What's the reason for that? The cosine and sine functions come from trigonometry. These functions allow us to split the amplification factor into two components based on the angle theta. If the wave direction aligns with the platform's natural oscillation, the amplification factor in that direction is maximized. The cosine and sine functions simply help us weigh how much each direction contributes to the total amplification. So the angle of the waves can either increase or decrease amplification effect depending on how they align with the platform's motion. Yeah, exactly. If the wave direction is aligned with the platform's natural oscillation, the response will be maximized. If it is at the right angle, the amplification will be much less.